Hello, this video covers using log graphs in experiments to find the relationships, or particularly the constants in relationships between variables. We see lots of physical phenomena where there are non-linear relationships: pressure, volume, radioactive decay, and each of them, if we graphed our results, we would get a curve like this. And what we want to do is make use of log graphs to get straight lines. That we've got techniques for finding best fits or doing regression lines. So let's work our way through the principles in the first video. Okay, so we see two groups of relationships in sort of physical phenomena. The first one I'm going to call power relationships. So y, whatever our output is some constant multiplied by x to a power n, hence I call it a power relationship. So you might think of that as in SUVAT, where you've got a t squared, or resistance, air resistance is v squared, say, and pressure volume equals a constant. Yeah, so you could have P equals, if we were doing this and we changed the volume in an experiment, we could see how the pressure went. So those are the exponential relationships, and now we've got the power relationships, and now we've got the exponential relationships. What's the difference here? Well, y equals again some constant multiplier, but now I've got another constant to the power x, because the growth rate or decay rate is proportional to the population at the time. So we see this in diseases like coronavirus or radioactive decay, and in finance you see it in investment, or you see it in returns on investment, or you actually see it as well in the depreciation of the value of an asset. So that's the sort of thing we're interested in, and for each one of these we want to convert these relationships at the top into linear relationships. Well, how do we do that? Well, we can log these equations. So let's have a look at the power relationship. So if I log this equation, on the left hand side I just get log y. On the right hand side there's k, the constant. Well, that just becomes a log k, and as it's multiplied by x to the n, it just becomes a plus, doesn't it? The multiplication becomes a plus. What happens to the x to the n? Well, that becomes n lots of log of x. So there we are with that one. On the right hand side, y equals kax a to the x. So left hand side again becomes log y. Once again, the log k that comes out on its own, and then again we get an addition operation, and now we've got a difference here because we now get x lots of some constant log a. So we've got linear relationships if we think about plotting log x on one axis. We're going to have a look at this in a sec, and they both got that, but on the power relationship we've got a log x here, and on the exponential relationship we've just got an ordinary x there, haven't we? So let's see how we can use that next. Okay, so if I take those relationships I just created and think about what will happen if I graph them in the right way. Well, on the left hand side I had log y, so if I make that my y-axis, I've dealt with that side. Looking at the right hand side, what's the variable? Well, the variable here was x, and the thing that's varying in this equation is log of x, so I'm going to, on my x-axis, I'm going to graph that as log x, and if I do that I'm going to have a straight line relationship. Hopefully my points, my experimental points, would all be on some line. Okay, so what do I do? What do I do next? I'm just going to have a look at the same point on exponentials. So again, I've got log y on this side, so my y-axis I'm going to graph as log y if I want to get a straight line. And on the right hand side, well, I've just got an ordinary x here, haven't I? I haven't got a log x, now I've got an x, so I could just put that on my x-axis. And if I do that and I plot my points, I should get some form of straight line relationship. So that's where we start from here. That's what we do. Now, if they're straight lines, they're both going to be y equals mx plus c. So let's do matching up some terms and see if we can find the m, the gradient, and c, the intercept stroke constant. Okay, so here, what's my y equivalent? Well, it's the log y, isn't it, in this graph equation above. What's my x? Well, the equivalent to that is the log x here, isn't it? Now, what's my gradient going to be then? Well, looking at the equation above, my gradient m should be n at the power. What's my constant going to be? Well, my constant is going to be this log k. That's unchanging, isn't it? So that's my constant. So what do I know? Well, I know that m, my gradient, is going to be equal to n, and my constant c is going to be equal to log k. And therefore, if I reverse those, if I find the m and c from my graph, then I can reverse that relationship and find out what my power is, because my power is going to be my gradient, and my constant out the front in this relationship is going to be 10 to the power of the constant, the intercept on my graph. Yeah, that will be my intercept there, wouldn't it? And there's going to be my c. So I can just substitute those values into this equation here, and I have an actual relationship with numbers in it, the actual values. Okay, looking at the right hand side, let's have a look at our exponential. We're going to look at the same thing. Y equals mx plus c is a straight line. So what's my y here? Well, that's going to be a log of y there. What's going to be my x? Well, here x is just going to be x, isn't it? They appear on both sides. So having matched that up, what's my gradient going to be? Well, my gradient on this one's going to be log of a. What's my constant going to be? Well, my constant again is going to be log of k. So that gives me these two equations below. Gradient equals log a, intercept constant equals log k. If I reverse those equations, then the a in my equation, in my relationship equation, is going to be equal to 10 to the power gradient, and k, the constant out front, is going to be 10 to the power of the intercept constant. So that's how we're going to use it. We can then substitute those values into y equals ka to the x. So there you have it. It's important that you can match the terms up here. This is where people struggle with it. Here's my summary slide, and you can pause the video and make a copy of this. This is probably the essential part, is being able to match up at this stage which term is which and which constant is which. In the second video, I'm going to use some examples to show how we do these. Thank you.